Today I will explain growth index theory of et al. Fundamental group. This will be very important for the proof and even for the construction of the homology. Okay, so what is the kind of, so given any x and of x with values in algebraically closed field need not be okay. Any algebraically closed field will pro-finite group, well, topological group, which happens to be pro-finite by 1 tal 1 x is base point x. So to explain the let's start with following elementary lemma. Let's take a discrete first. This is your baby example. And consider the category of G sets. So this is the category with an action of G. And then, so we have, we consider functor. I will usually refer to this as a functor from this category, just to the category of sets that takes G set X well, just forget the action to the underlying set, right? So, so this is a functor, and I want to consider the group of automorphism of this functor, right? Whenever I have functor between two categories, I can talk about automorphisms. So, and my lemma, first baby exercise in category theory, so that there is a canonical isomorphism between the group G and this group automorphism of the fiber functor. All right? Proof. It starts with a construction. I need to explain how this homomorphism. So, G in G, I need to produce for you an automorphism of the fiber functor. So I have X in G sets. So this is a set with action of G, and I want to produce an automorphism of this set, which is natural in the sense that it's it computes with two morphisms in the category of G sets. So what can I do? I don't have that much structure, so well, underlying set of a set, so gx here, so let's just define this to be the action of. So if I have a morphism from x to y, or from x to x prime in G sets, and the following diagram is commutative, so let's call it F, then, oh, maybe, sorry, let's call it pi. Then, by definition of a morphism in the category of G sets, this diagram is commutative. Right? So this defines a map from G to this group.
G sets are left G sets.
Well, G is a group, so I can identify the opposite group if you wish. But
otherwise, it won't be commutable.
what?
But you have to fix it. The G set has
Well, this is I have only one action of G here, right? So you're asking whether I should not. Let's prove that this map, so this defines this map. This defines this homomorphism star. And now let's prove that it's an isomorphism. Well, so the observation is following that, consider G itself as a G set. Well, for example, I can look at the left action. Then, so let's observe that f of x is, so f is a functor from a category of sets, and I claim that it's representable. So this is morphisms in the category of G sets from G to X. Namely, so any such morphism is determined by the image of identity here, right? So, and therefore, this shows so by Yoneda lemma, automorphism of a representable functor, the group of automorphisms, is the same as I will put this area here. Is the same of G, right? Namely, we have, strictly speaking, I should put, if I have an automorphism of this object, definitely it acts, every automorphism of this object acts on the functor. Вот это. Ну, а что такое задать отображение из такого G-множества? Я утверждаю, что этот G здесь действует свободно. Да, это как бы такое... То же самое, что задать образ единиц. Если я скажу, куда единица переходит, любой элемент, любой другой элемент, я уже знаю, куда переходит. Ну вот, поэтому такие отображения из G в X — это то же самое, что точки X.
Хорошо.
Поэтому получается такое равенство. Okay? Questions here? Stepan, maybe you would like me to put here opposite, but it doesn't really matter because it's group.
You're just restating Cayley's theorem
Yeah, yeah. So, and now so what is automorphism of this G set? What is this? What are morphisms from G to itself in the category of G sets?
You're actually applying Kelly's theory.
Well, I'm applying Yaneda level.
Every is right multiplication by
Yes, yes. Okay, so this is G. So we have a map from G to this, and it's immediate to check that it's the same map as we constructed here, but by Yaneda lemma we know that it's an isomorphism. So complete the proof.
No, I mean, if G is a monoid, just does not prove that this word fine. Right?
Yes. Okay. But we have a group. So, now, very good. So let me explain how we consider this. So let's consider the following example. Let T be a nice topological space, connected topological space. Well, the word nice here means that it's locally contractible. Weaker assumptions are enough assumption, but let's say locally contractible here. So, okay, then, and suppose I have, this is important, and suppose I have any point in T. Then, as we learn from algebraic topology, the category of covers of over T. So what is a cover? It's a map from which is locally on T looks like the direct product of a discrete set, possibly infinite, and the base is equivalent to the category of TA sets. Right? So maybe I will. So there is this equivalence, and this category has a map to sets that takes, I will call it FA. This category also has the forgetful map, forgetful factor to sets. Now, what is FA? So a cover to T. Let me see what is the name I want to use it. Okay, that will be P. So then FA of this cover, that's an object here, is just pi the fiber, pi inverse of A. That's the source of the terminology. It's the fiber factor over A. So, and I claim that there exists an equivalence of categories that makes this diagram commutative. So let's see how it works. So first of all, I claim that if this is a cover, then this set is equipped with an action of pi 1. Let's recall how it works. So, picture. So suppose I have a base. This is my T. I have a point A, and it can be something very, very complicated. Now suppose I have a path. Right? And now here I have and so I have some this fiber, endow this fiber with an action of pi1. Okay? So here is, I have a path gamma, which represents an element of pi1, and I want to define action on this set. So I give myself B, and what I can do, I can think of this path as an element, as a continuous map from the closed interval 0, 1 to the base, and I can lift it, right? So that's a bit of covers that any path can be lifted. I can lift, right? So yeah, maybe I should. This. So this is again. If I fix where the initial point goes, right? If I fix the the beginning of this path, then so the lift is uniquely determined by gamma and this point B. So this, okay? Does it make sense? So this construction depends only on the homotopy class of gamma, and it defines this map. Okay? So now let me explain how you construct the inverse map, the inverse functor, right? This gives me a functor in one direction. I can produce a functor in the other direction. So functor in the other direction. Okay? So fix a universal cover. Okay? And the point tilde in this universal cover with which is in the phi over A. So right. Then this choice of this point determines an isomorphism between automorphism group of this cover, so the group of deck transformation. So in the category of covers, of this universal cover, and pi1, right? So, well, how it works? So the point is that for this what's called a Galois cover or normal cover, so the automorphism acts simply on the fiber. So if I have an automorphism, I look where this point A tilde goes. So it goes to another element of the same fiber, and I can write it uniquely as some element of pi 1 acted upon A tilde. And this gives me this map. So automorphism of this cover is a fundamental group. So in other words, this is a torsor over this guy. So the group acts here. Okay? And now whenever I have a torsor over the group, so suppose I have now X in pi 1 sets, TA, I can do the following. I will, so given a set with action of pi 1, I want to construct another cover. What can I do? I can simply take U, okay, maybe it will not be visible. So when I have X, I want to assign to X the following cover. I take the torsor cover. This is a torsor over pi 1, and I have X. And what I can do, I can take product. Right? So if you have a torsor group and a set on which the group acts, I can kind of form this product. What is it? It's a, you take the Cartesian product, right? And now you have two action. So this is U universal times X. Now you have two action of pi 1 here, here, and here. You take the diagonal action, right? You act, so you consider this as a space with action of pi 1, the diagonal action, and you quotient it by pi 1. That's the construction. So this defines the inverse factor. So I explained this commutative diagram. Further, we see that a fundamental group of topological space can be canonically recovered from the category of covers and equate with this fiber functor as automorphism group of the fiber functor. Right? That's combination of this statement and the lemma. So that's kind of we should find. So I want to kind of extend it to use a similar approach, but it will be more involved. So first of all, we should have to deal not with discrete groups, but random groups. So, and so this is the next section. So let's now G be a topological group, and this time, so I want to consider the category of, by definition, this is category of sets with a continuous action of. So what it means is that the map from the action map, this map, is continuous. Right?
X is what topological.
Yeah, X is a discrete set. Discrete. This is discrete. Yeah, good. We only consider discrete set space. Only consider action on topological spaces with discrete topology. Okay, so inside this case, we'll look at the category of finite sets, finite G sets. So just X is finite. Okay. Now, that's one construction. Another construction that I will need is so I have this category is forgetful functor f to just category of finite sets. Finite sets. And I want to prove a lemma analogous to the first lemma that we discussed at the beginning. So I want to compute the automorphism group of this functor. This setting, G is any topological group. So, so here is, in order to formulate the answer, clearly, I should not expect to recover G. For example, if G is a connected group, like circle, then it cannot act on a discrete set, right? So category of finite G sets would be trivial. So nothing interesting happens. So okay. I will define profinite completion of G. Well, this will be another topological and it's defined as follows. It's limit, inverse limit over all normal subgroups. So this is this stands for normal groups of open normal subgroups of finite index. Finite index. Right? And I will take G mod U. So this is a finite group where its quotient topology is discrete. It's open. I want to think of this as a topological group. Basis of topology. Well, what is it? It's G on this profinite completion is simply the kernel is given by the kernels of the map from G to G mod U, right? So if I have an element of this inductive limit, I can project it for every U. I can project it to the corresponding component, get this map, and I take the kernel. Good. And this is a topological group which is, by very construction, is a profinite. Again, profinite group is, by definition, is a topological group which is isomorphic as a topological group to the inverse limit of with respect to a directed system of indices. Directed means that every two elements have upper bound. You have two open normal subgroups of finite index with this property, then they in open and finite index normal, therefore this is a directed set. Okay, so good. And so we have, so as you see there, kind of the topology on this on this inverse limit depends only on induced by the what's called the Tikhonev topology on the product of these finite sets. But really, this set of indices depends on topology on G. I take only open subgroups here. So I have a map, an obvious map from G. Continuous. It's clear from this definition, and it has universal property. So universal property. Well, whenever you have a homomorphism H from G to H, where H is profinite, and this is continuous, there exists a unique continuous homomorphism that makes this diagram positive. So this is the recipient of universal map to a profinite group. And now I can state the analog of an analog of this first lemma. Да, но как-то, ну, это плагин. Okay, so what is the statement? Lemma is that the automorphism of my fiber functor is precisely this profinite completion. Okay, so well, before I actually give a proof, I need to explain so I explained what this means. This is a profinite group. I also want to make this into a profinite group. So the statement is that there is a continuous, well, that's isomorphism of topological groups, right? So let me explain how to put a topology here. So that's, and then how to construct a map is that basis of topology on here is given by the following subgroups. You take for any set finite G set X, finite G. You can consider the kernel of the map from the automorphism group of F to automorphism of finite sets, of a finite set, f of x, right? It is such a map by definition. So the topology again is formed by subgroups of finite index. This is a finite group.
You mean by their pole-sets?
By what?
By pole-sets of such subgroups.
Yes, right. Base of topology of neighborhoods of the. Okay, good. So now, so this is a. This makes the automorphism of F in a finite group. It's just equal to well, this automorphism equal inductive limit of over all x of this finite quotients. Okay.
How do you make all axes into the diagram?
Say it again.
How do you make all axes into a directed diagram?
That's a good question. So yes. Okay. What should I say here? So you say that you look at all x and you introduce the following partial order on this set of objects. One object is a subset of another if an embed x inter prime. This is a partial.
Have an automorphism of a larger object is not obliged to preserve the smaller subobject. You can't map an automorphism with larger objects.
No, I think. Let's see. No, I think. Okay, if I have a map from x to x prime in the category of G, then well, so automorphism of f act here and here. Well, so sorry. So I said that so x is less or equal than x prime if there exists an embedding of G sets.
Wait, so automorphism of f is just from f of x to f of x.
Yes, yes. So we say that. So the question is, what is really the limit? Is The partial order is the following. So we say that x is less or equal than x prime if there exists an embedding of G sets.
Okay, and you wish this diagram to be contravariant.
So
Have an automorphism of x prime, you wish to produce an automorphism of x. How do you do that?
no, I don't want this. I only
You need a diagram of finite groups.
no. So I need this to be. So what I want is automorphism of morphism. So what I want is this map, right? So all I need is I will take the identity map from this guy to this guy, and all I need to assure is that this subgroup goes to this subgroup.
But by the homomorphism theorem, this is just the automorphism of x prime.
This is not. This is the kernel.
Oh, this is the image of. So what? It's not.
So if I have automorphism of my fiber functor that acts as identity here, it's not surjective.
What f of x?
Does it make sense?
Yeah.
So now let's now give a proof. So proof, well, first I need to produce a map, right? And a map automorphism of f. So is the construction as before. So if you have an object, G set x, you just, in an element of G, you just assign to it the action of G on x, the given action. So this is continuous homomorphism, right? And then, because it's profined by the universal property, it factors. So this gives me a map. Now, let's look that this is an isomorphism. So I need some names. Okay, so map I, right? So phi is injective. Okay, so phi is injective. Okay, so normal subgroup or subgroup finite quotient. So we need over there. So this quotient can be viewed G set, finite G set. So what I'm supposed to do, I'm supposed to show that for every element here, which is not identity, there exists a finite G set on which this element does not act trivially. And my G set that I'm going, well, so I take an element here, right? So it's an element of this inverse set. So at least one coordinate is not equal to the identity. So I pick this U. Now I will produce for you this element does not act trivially. Okay, so quotient, so it's a quotient.
Извините,
Да.
сейчас такой вопрос. Ну, вообще то, что это инъективное и субъективное, это мы знаем.
Ну,
Потому что сама же отображается. Тут весь вопрос в том, что это отображение, оно гомеоморфизм, то есть обратное не требует.
Нет, но что значит? Неправда, что G отображается сюда и еще. То вот это отображение нулевое, тождественно.
Извиняюсь, оно является биекцией на компонентах связанности G. Вот что мы знаем.
Ну, я не знаю, что значит ну, не очень мне хочется. Не, это не очень хорошо. Вообще в G может не быть, например, если G это дискретная группа, простая группа, типа там SLN Z для больших. Ну нет, сейчас. Ну, бывают дискретные, бесконечные. Бывают группы, у которых нет вообще нормальных подгрупп конечного индекса.
Например, группа рациональных чисел.
Да, прекрасный пример. Поэтому тогда это вообще будет 0. Утверждение неверно, что это зависит только от группы связанных компонентов. Вот. Okay, so let's take this G set, and then what we have. Homomorphism from our homomorphism for finite completion to automorphism in the category of G sets. So G sets of G mod U. Right, so I I take this is my phi is completion to the automorphism of the functions, in particular it and this is easy. So what is an automorphism? So I have also right action of G here, which commutes with the left action, and U acts trivially. So this is G mod U. Right? So I have this commutative diagram, and this is an isomorphism. Right? So in particular, if I have an element which projects to non-identity element here, it's also non-trivial here, which implies the injectivity. Now let's prove surjectivity. Okay. Да, мы выбираем такое, нет, наоборот. Допустим, что у меня есть элемент здесь, такое, что φ переводит его в единицу. То есть на конечном G-множестве этот элемент действует тривиально. Тогда мы выбираем такой U, значит, наш элемент, мы предположили, что элемент здесь это не один. Мы выбрали такой U, что вот одна координата, вот эта вот, она не равняется единице. Теперь рассмотрим конкретное конечное G-множество. Да. Чудесно. Okay. So, phi is surjective. Okay. So what we have here? So G, this profinite completion is compact, right? Because it's a closed subset. It's the theorem of Tikhonov. So it's a closed subset of a direct product of finite sets, infinite direct product. It's known that it's compact with this Tikhonov topology. So G this is compact. Therefore, enough to check that image of right, and definition it amounts to the following. So for this property is equivalent to the following, that in G sets, finite G set, and any gamma, which is an automorphism of this fiber functor, there exists such that following is true. So, I have F, I have a G set, and I have an automorphism of this fiber functor, so it gives me this automorphism of this finite set. And on the other hand, I have an and I want this to be equal. So, so if I can show, this will prove that even the of G here is dense, right? So the topology on this limit it's so that well, density is equivalent to say precisely well this property. Let's check this. That's the content of the statement. Okay, so let's take for U, let's define, so let's take for U the kernel of the map from G to the automorphism of finite set, F of, right? So how, yeah, so there's X is this G set, finite G set, so we have a homomorphism, continuous homomorphism from G to this finite group. Its kernel is going to be open because it's continuous, so this is, it will have finite index because this is finite again. Okay, so then, so let's just look at the diagram. So we have finite G sets. We have also finite G mod U sets. This is now a discrete finite group. And we have, well, every set with an action of this finite group can be considered as a G set, right, via the projection. So here I have well, I have a commutative diagram. So that's the forgetful function. Okay, and this diagram, so let's call this F, and this is F bar. And now this gives me automorphism of to the group of automorphisms of F bar. Right? So if I have, just the commutative diagram. And so here I have G that maps here. And here I have G mod U that maps here. Commutative diagram. And by the first lemma that we proved, right, this is G mod U now is a discrete group. Yeah, so forget about topology. We know that automorphism of this fiber functor is precisely G mod U. This is an isomorphism. So that in particular means that this map here is surjective. So, okay, so you take gamma. This is, well, an automorphism of this fiber function. You look at its image here, and you lift it via this surjection to some G. So this is gamma bar here, and this is G that maps here, and this proves surjectivity. Okay, so now so what is our next goal is going to be to invert this procedure. Invert this procedure. So what does it mean? Okay. Suppose now that we start with any category C, and a functor from this category to the category of, say, finite sets. Then I can still consider automorphisms of this fiber functor. That's a group, a topological group. Speaking of topology, and I have I can sort of promote this functor, right, to a functor from to finite sets equipped with action of this group, right? There is a tautological sort of, I have, this is quality, and that this is the forgetful functor, right? So for any C and any such functor, I can, well, endow, so how this works. So if you have an object X, what is the corresponding finite set with an action of the automorphism? Well, if you have an object X, you just assign to it f of x, which is, first of all, it's a finite set, and secondly, it's equipped with an action of the automorphism of f by definition. So what is the goal? The goal is to, well, see whether this equivalence of categories, or rather, so let's give a name to this. C, so goal is well, give conditions equivalent. Okay?
I want to kind of adjust to this subject post of F, so will this be clear in our applications that C is a small category? Because you can't just...
Well, C is maybe small category. Yeah, yes. So the objection is that a kind of, so if the set of objects is not as, well, if class of objects is not a set, then maybe you can't really take the limit. Yeah. So, and this is what I will state this conditions now. It will take some time. Okay, so first, a bit more categorical definitions, a bit more category here. So, let's suppose I have any functor from so from two categories, A and B, a functor. So I want to say what does it mean for a functor to be exact. What it means for a functor to be exact. So first, if A has finite products. Well, again, this is a, so what it means, this condition that it has this finite products is equivalent to two conditions, that A has final. Final is a limit over empty diagram. Final object. Okay, maybe. And finite and fiber products. Fiber products. Fiber products X, Y, Z. Okay? It's limit over the following diagram. You take X, Y, Z. If you take the limit over this diagram, that's by definition called the fiber product. Morphisms from any object W to these two guys is the same as pair of morphism to X and to Y, such that the composition with maps. Finite, yes, thank you very much. Finite limits, yes, not only products, limits. Yeah. Thank you. Very important correction. Thank you for catching this. So, F commutes with them. Right? What it means that it commutes to them, it means that F of final object is equal to the final object in B, in particular it exists, and secondly, the map from F of X, F of Y, f of z is isomorphic to f of x, y, z, right? Then f is left exact, right? So left exactness means for any function that has commutes with finite limits, right? That's first part of the definition. And second part, well, two, if A has full limits, and again this condition is equivalent in that you have the initial object think of A as a category of G set. Well, the initial object is going to be what? The initial object is going to be empty set, and the final object, what is the final object in the category of G sets? Point. Yeah. And well, co-products x, y, z. Well, fiber co-products. And f commutes with them. Then that f is so f is exact. And left. Exact. All right? Now, now I can state, well, again, definition, the main definition of today's lecture. So I suppose I have a category suppose I have a functor from a category to the category, from a category C to the category of finite sets. We will say that the pair consisting of C and F is a Galois category if it has the following, satisfies the following condition. So C has finite limits and finite limits and all limits. F is exact. Secondly, every object D is, well, finite coproduct of connected objects. Okay, so what is a connected object? So X, context of this definition, X is connected if, well, first of all, X is not the initial object. And for every monomorphism, either X prime empty, initial object, or X prime is X. So, okay, so example to have in mind here. So let's say that C is a category of G sets. And this finite G sets. And this is the forgetful functor. What are connected objects? Say it again. Правда? То есть мы хотим такие одна орбита, да? То есть мы хотим, чтобы в нашем множестве не было никаких нетривиальных подмножеств. Это означает, что там одна орбита. А почему такая терминология? What is the source of this terminology? So remember that pi1 set topological space is the same as covers. And the cover is connected if and only if the action of pi1 is transitive. Okay, so now third definition, the third problem is that so F reflects isomorphisms. So what it means is that if you have a morphism from X to Y, then F of A is isomorphism if and only if A. Okay. So this is called polar category.
Abelian setting, which like the definitions that are modeled from, if a functor is exact, then it obviously is isomorphic. So if like this is not true in this sort of setting.
Yeah, it's just well trivial functor. Everything is maybe too empty.
Oh, so even in the abelian setting you can have the functor.
Yeah, you're right.
Not injected at all. Oh.
So, good. So, and here is the theorem. Which is due to Grothendieck. And that's why we introduce all this. So, if C F is a Galois category, then that we had over category 2. Sets equipped with an group continuous action. Again, this is a profinite group. Well, is an equivalence. So there is a finite sets. Sets. This is the forgetful function. So, okay. In this case, C is determined by this the automorphism. Okay, so I will. The proof is not out. It's I will start proving this. But I have only 3 minutes, so I will prove I think 1/3 of the theorem, because it's just a category theory. It cannot be that difficult. We don't have that many ingredients here. So beginning of proof. So what? Well, I will prove the following lemma. So two morphisms, A and B, from X to Y in my category, right? And X is connected. Then, if, so let's apply our functor f to these morphisms. So this is going to be, this is automorphism of, well, this is a morphism from f of x between finite sets, f of x and f of y. So let's take some point x in f of x, and let's assume that following equality. Yeah? So f of a, f of b, these are just morphisms from f of x to f of y. So it makes sense. Then A is equal to B. Proof? Okay. So let's consider equalizer of A and B. So what does it mean, equalizer? Equalizer is just the fiber product, right? So you have a map from x to y times y, and you take the fiber product with the diagonal, right? Equalizer. This is kind of, yeah. So equalizer is a limit, and so our functor commutes with limits. So I know that if I apply f to this equalizer, it's the same as taking equalizer of f of a and f of b, right? So so I have here two what is the equalizer? Equalizer here is the subset here where the two maps are equal. So this condition tells me that this set is not empty because X. So that means that this is also, this implies that this equalizer is not empty. So it's not the initial object. On the other hand, the equalizer is always admits a monomorphism to X. So, and now let's look at the, remember, let's know the definition of a connected object. If I have a monomorphism from an object to a connected object, and this object is not initial, is not empty, then it's either isomorphism or, well, it must be an isomorphism. So, therefore, equalizer in B is X, since X is connected, and this in A is equal to. So, corollary of this lemma is that we have the functor is faithful. So if two morphisms are equal after application of F, then there are equal region 4. So why is that? So so it's enough to check this for connected X because any object is coproduct of connected ones, finite coproducts of. So, but for connected X, it's, as you see by the lemma, it's, well, so if f of A is equal to f of B, if the two morphisms are equal after application of f, in particular, I can take any X. This will be true. So, and then it implies that A is equal to B. So, okay, so I proved, well, 1/3 of the statement. I proved that it's faithful. You need to show that it's fully faithful and surjective on objects, isomorphism classical object. So I would, I will not explain the rest of the argument because I want to move to geometry next tomorrow. So it would be, it's possible to leave, I would leave it as an exercise, but probably there are more sort of important exercises to do. So let's leave it as it is. So next time, tomorrow, we will apply it, this general construction to construct all fundamental groups and study its basic properties. Thank you. Questions? Да. Да. Сейчас. Нет, копродукт это такая ни над чем. Это не... Бывают еще такие как бы корослойные, да, когда вы берете. Там можно чем угодно брать. Да. Как бы дизъюнтное объединение, так сказать, в категории множеств, это было бы дизъюнтное объединение. More questions? Да. Ага, ну хорошо. So,
Можно спросить?
Да.
А вот, допустим, у нас есть два файбер-функтора.
Да.
Тогда это задает на C две структуры моноидальной категории. Правильно? Ну, у нас же множество же есть.
А при чем тут,
моноидальный.
на C две структуры моноидальных категорий? Очень хорошо, да.
Да. Вот, видимо, правда, что они могут совпадать.
Правда. Мы в следующий раз, я обещал теории категорий закончить, но, значит, будет еще одно. Значит, утверждается, что любые, что если у вас есть две пары C и F, и C и F', то есть C одинаковые, а F и F' разные, но я предполагаю, что все они категории ГЛО, то тогда функтор F совпадает с функтором F'. Он изоморфен функтору F'. То есть, ну вот представьте себе, что у вас есть категория накрытий над связанным топологическим пространством. Тогда для каждой точки базы, для каждой точки топологического пространства у вас есть, значит, вот возникает этот функтор F, конечное множество. Ну, в множество просто. Но если топологическое пространство, значит, связано, то эти два функтора изоморфны. Нет никакого канонического изоморфизма, но, значит, этот изоморфизм зависит. Ну и отсюда, значит, это тоже категорное утверждение для любой категории ГЛА, что два таких, так сказать, они ковалентны, это важное утверждение. Но и отсюда следует то утверждение, про которое вы спрашиваете, что две моноидальные структуры совпадают. Но очень хороший вопрос.
Ну, в смысле, будет просто изоморфизм
Да,
друг?
да, да.
Хорошо, спасибо.